Hey guys, what's up? Eddie Aho here with KissAnalog.com. So today what we're going to do is we're going to look at this Nice Power supply. It's actually brand name, Nice Power. Did a review on this, and I thought it'd be a great way to teach something more about power supplies, okay? I'm going to talk about the layout of the design, and we're going to talk about flyback converters, and hopefully I'll make the flyback converters simple enough, this conversation, that even the newcomer will understand, will be able to grasp some of it, okay? And then also for people that are more advanced, just another look, and maybe I'll have some more insight, okay? But we're going to talk about the layout and so on, and I think it should be interesting. Teach you something about switch mode power supplies. So let's just jump in and do this thing. All right, I got this little whiteboard here. Hopefully you can see that without too much glare. Get the glare off there. This part's pretty simple, right? We got an EMI filter on the input. AC power comes in, goes through an EMI filter, goes through an AC-DC stage, which is essentially your bridge rectifier and your bulk capacitor in a lot of cases. In this case, that's what we have, okay? So then I kind of drew a little bit of a circuit here. Got a transformer with a FET that switches. So we have a bulk capacitor over here. Now we have DC voltage, but now we kind of turn it back into AC again. We don't like the 60 hertz or the 50 hertz, too slow. So now we're going to switch, say, 100 kilohertz, something 1,000 times faster. So this transistor is going to do that for us. Now we can use a small transformer. In the old days, like my big power supplies back here on the bench, they just have big old transformers that do this, and they do it 60 hertz. But if you switch faster, you can make your magnetic smaller, your transformer smaller. That's the idea of switching power supply. You can also make your capacitor smaller. It's easier to filter and so on. So we're also going to get isolation because we're going to use a transformer, right? So we're using a transformer, we're switching real fast. On the output of this, we can have lower voltages. So we actually have two power supplies inside this bench supply. We have the one that is supplying our output, our regulated voltage that we can vary from 0 to 30 volts, right? But we also have something else. Let me get to that. But one more stage. We have LC filter. We have some filtering. After we do this, we want to filter that high frequency stuff, right? So we also have to have some bulk capacitors. So we come off this with some, again, AC to DC. We're going to AC to DC on this side of the isolation transformer. So we're going to have some diodes and then bulk capacitors and then some high frequency filtering, some LC filtering. So let me jump into what else we might have down here. Okay, I'm back. I've added a few blocks. Now, off this EMI filter, this particular design, we're going to go through another small EMI filter for this housekeeping power supply, we're going to call it. It's a flyback converter, but we're going to go through an AC-DC, get that bulk voltage that we can use to switch. And instead of this converter, whatever that converter is in the main power stage, we're going to have a flyback in this one, okay? And then on the flyback, we might have several outputs. And those outputs, well, here's some other auxiliary circuits, let's call them. Voltage regulation circuit, so we can control the voltage that comes to our output. Current regulation, so we're going to have some voltage and current controls because we have those knobs on the front of the power supply. We're going to have a display, right? And we also might have some auxiliary power to not only just power these things, these guys are going to be powered, but we also are going to probably have a voltage feedback to power the actual flyback converter. Okay, so one of these outputs probably come right back and power this guy, and we might even have something that powers this guy. We don't know yet. So we'll look in that later, but today what we're going to do is I'm going to kind of show you the overall layout, and I'm going to talk about this branch right here. We're going to go through this EMI, through this, and talk about the flyback. All right? Quick. I just want to go over this and just kind of point out something. You've got your schematic generated, right? You've designed that. Then you want to start designing your circuit board. So you want to place your parts. First of all, you want to kind of think of your schematic as these groups. Things that are important to stay close to each other, and then you can connect them, and you think about, well, Now I'm just showing a line. It's not power. It's just how these things are connected. You'd have you know, 2 lines plus and a return coming through all these things. You want to think about how that loop is going to look. If that loop is out here, goes to your load and comes right back, that's great. But if that loop goes all around a board and then zigzags back, it's not as good. You know, for EMI, for noise. So, and coupling, you're going to couple things in other circuits, right? So you want to keep these blocks kind of together and kind of separated from the others. And if you can, you want to have these things basically left to right or right to left, up to down, down. You know, you want to have a straight line, okay? Okay, so for instance, if you're going to break off and come down here and have this housekeeping supply, you know, it's the voltages, keep all your housekeeping stuff, right? If this flyback is that circuit, and you have an EMI, some filtering, you got this EMI filter, but you're going to do a little more filtering. The reason you don't want this noise coming back this way into the circuit, and you don't want this noise coming back into here. So you want to protect these circuits from each other, and by disturbing anything downstream either, you know, both. So this circuit, it would have this filter and that filter to get outside, but it has one filter between these two. So that's a nice thing to have. But you don't want to place this EMI filter up here physically, right? Because then how are you going to route, like I say, each one of these are going to have a plus and minus, right? A plus, you know, power and return, let's call it. And so you don't want to have a power and return crossing through all this stuff, because the whole idea of using this filter is to keep this noise off of this stuff and this stuff off of that. So if you have your EMI filter up here, now you've cleaned this to go into here, but you're going to run this power from here to here. That doesn't make sense, right? So anyway, you got to think about things like that. And then within each block or each function, you want to be careful to think about those things too. You want to keep things short. You want to think about how the current's going to circulate through from input to output. Now see, since we have isolation here, we want to think about this loop here, and we want to think about this loop here. Okay, let's go look at the board. All right, guys, so we got the power supply here all opened up, and we want to just kind of take a look at those blocks that were in that board that I showed you, and kind of how they fit in here, like how well they did on the placement and the layout. And there might have been competing requirements, like the fan, right? They probably the best place to put it back here. On top, it could get covered. There's some vents on the side of the metal box. So we got vents here on the side, and we got the fan in the back. So yeah, the front's taken up, and the top and the bottom probably aren't the best places. So stick the fan in the middle. We're going to want to get the heatsink cooled. We're going to want to get all these power parts cooled, so they're all kind of put around the fan. So, okay, but does that give us the right placement for the power, to keep the power integrity or the signal integrity, meaning that the power or the signals coming in and out, are they going to go in without being coupled to other things and getting muddied up, you know? And so we have a power switch up here in the top right corner, but the power input is down here in this corner over here. So the power has to go all the way over here to get turned on. It's like, well, it might have been better to put the power switch over on this side, right? We got the DC output over on this corner, and we have the low voltage DC circuitry here. That looks good, but then we also have the low voltage DC output here at the front panel right next to the AC. And also where the AC enters the board is right here. Here's the EMI filters. So we're going to take a closer look. We're going to zoom in on this, and we're going to take a close look, and I'm going to kind of point out and show you what the circuitry looks like, okay? Let's go ahead and do that. All right, so to begin with, our front plate, okay? There's our display. Our outputs right here. We have a ground here for chassis ground, and we have our current on this side and voltage on this side, and our power switch right here. And then we have this nice big display. So yeah, that looks nice. And if the power switch had been put over here, then this, maybe all this stuff, so you can kind of see, because of the display taking up this section, it's like, well, where do we put this stuff? Those are what we call competing requirements, Now we look at the back, AC power comes on this, the IEC connector has a fuse in this connector, which is nice. The fan is installed nicely. It's got this cutout at the bottom of the box right here, so it kind of protrudes there, so it's held very securely in place, right? Then we have this big beefy output terminal, so input, output separated. That's nice. Now let's look inside the box and see how things are routed and assembled, okay? All right, so let's just kind of walk through the circuit, and I'm going to just kind of point out some things that could have maybe been done better. But there's also challenges, like we say, because the fan and so on, and the placement of certain things want to be near the fan, maybe. Do they really need to be? Now, one thing I can tell you in using this is a fan, I have to be running half power or more for some period of time before the fan turns on, then it turns on for just a moment, turns right back off. So I'm just wondering how critical it is or was to put all the hot stuff right up next to the fan. Okay. Now, one thing about the fan I want to say is it pulls air out of the box. So the fins around the side is going to pull air across this way through the fan out. So this is going to be cooled. These things are going to be cooled. From this side, of course, we're going to get cooling across transform the magnetics as they exit the fan. So the traffic area is close to the fan. So it is kind of nice to have it there. No question. But because this stuff seems to be designed very well, the size of components, they're not undersized, except for the ceramic resistors. I don't know why, but so many people will design them to take half their power, and they're going to run super hot when you do that. So D-rays is, I know they teach that in school and everything, but it's just, and I've even heard some vendors say, oh yeah, half power is fine. Well, yeah, if you want to run things super hot, but run the power of the resistors, say 1/4 or 1/3 the rated power at the most, and they'll run a lot cooler. They're cheap and relative to other parts, and going up one more power range or wattage, whatever, isn't a big deal. Let's just look at these ceramic resistors since I'm talking about them. Here, let me give you a close-up. See, there's two of them right here, right? And there's no space between them. I think there should be space between them, and also space between them and the board, so they have air that can circulate around them, okay? So they run hot, and then there's a single guy over here. He could have had another one stacked on top of him, and he could have been mounted up off the board. So things like that. Okay, so let's get back to talking about the layout and stuff, okay? All right, so power comes in right here, okay? It comes in, runs down these wires, down along the chassis, and then across, and it goes through all these cables. See how it runs through the cables? And then it comes up here. One of them comes up here to the switch, either line or neutral. Haven't really tried to figure out what that is right yet. But and then it comes down to one side of that yellow capacitor. That's the next capacitor. It's across the lines, okay? And the black one that came down along here just runs straight through all this mess again, through all these cables, and then comes up and goes in to the other side of the capacitor. What we end up with is red and black power coming into this first X capacitor, which is great. That's the way it should be. And then combo choke just perfectly placed. One choke is on this side, one choke is on this side. So they're separated, and they have a plastic over the ferrite or whatever it is, all for isolation purposes, because we're on the high voltage side. Well, relative high voltage, 120, 240 or whatever. All right, so then we come out and we go through another capacitor. And by the way, when we're talking about voltage, this particular one is rated for 120 volts, okay? Now, they may have a version that comes for 220. But anyway, we'll talk about that in a little bit. But EMI, so power comes in, goes straight to the EMI filter, which is awesome. But then what's really weird is it goes through a fuse, and then it goes back through another combo choke, an X cap, and a bridge rectifier, this little small bridge rectifier here, and then a bulk capacitor. So we have a DC supply. We have a DC supply that we've generated that's right next to the AC supply coming in. So it does this real tight loop to this corner. And what's additionally weird about that, instead of just having this fuse and this stuff running a different direction, instead of wrapping back around to the input of the EMI filter, now we have input and output right next to each other. Additionally, is that it's on this side of the main big EMI filter, because over here, this is the transformer for the flyback converter. This is the control chip for the flyback converter right here. Okay, right there, that little black guy right there. So we have our transformer, our controller, and our output diodes right here, which we'll talk about in a minute. But anyway, so this guy's powering that circuit. So that's really weird that you'd run your main power this way to what's going to go over eventually over here to your bulk capacitors, and then you straddle this guy. Not only do you go from output to input, now you're straddling this across here, so you're crossing the input again. That's all kinds of EMI wrong. Yeah, you don't like to do that. All right, so let's just go back to the overall circuit. All right, so continuing on, we see the EMI filters over here. We see the flyback transformer here and the controller chip right there. This guy's the big thermistor. It's a negative temperature coefficient, meaning it has higher resistance until the inrush current. So what it is intended to do is the current comes through this EMI filter, comes over to charge these bulk capacitors, it limits the inrush current. As it heats up, the resistance drops down, and that's the way it works. Okay, so now let's just say, in contrast to that, we also have a PTC up here. So the output circuitry is right here, the output filter. In that block diagram, this would be the output LC filter. Well, we're going to have some diodes under the heatsink here. We have some big heavy wire here. Okay, just bring that up close so you can see the output section. So the output section, we have big heavy wires from the transformer come down to the board. They're going to come over here to some rectifiers, and then come over here to the bulk capacitors, well, the LC filters. You see the two L's. So there's two outputs off the transformer. They both get LC filtered to the output. And then there's a current shut down here. There's parallel wires there. And that's just a nice way for when you have a lot of current, say 20 amps in this case, going through this, that you don't have to drop very much voltage across there. And there's enough voltage sense for the chip to control the current. Okay, now then what happens, it goes to these big terminals over here. Okay, but then we also pick up the red one, and it goes back down the chassis here to the output terminal. The red and black do, but the red one goes to this PTC, this positive temperature coefficient. That's opposite of the NTC, the negative temperature coefficient. This one is a resettable fuse, is often called. Okay, and I think Raychem is the one that patented that years ago, but now everybody uses it because the patents ran out. But anyway, so then power runs up this way. So as the power runs up there, we have our black and red wire right here. Okay, and it would have been nice to twist these wires together instead of just leave them alone like that. Okay, that would have been nice to twist them. And it is nice that they ran them along the metal here. Okay, let the metal be like kind of a shield in a way. But then the problem is we come up here and we tie wrap it to AC power. The red one come down to the board, and the green one, the chassis. So that's unfortunate. That's a simple thing to correct. We're gonna correct that. In another video, I'll do all these corrections, okay? But I'm just showing you layout and placement and the design of the box for now. Okay, so we come back and look at the entire thing. Now, well, since we're talking about wires and coupling, when those AC wires came in from the AC port right here, comes in here, and then we get these wires here that run up to the chassis. They go through all our low voltage stuff, going to our display, our flat cables. We have our voltage and our current pots right here, and the wires from those are all coupled into here. So we're coupling all our AC power as it crosses through all this stuff. And one of the wires comes up to the switch, the other one just comes directly there. But we can correct that too. We can help fix that. It's nice that they run it along the metal, but then the fan power comes running right back down here to run and power the fan. We don't want to couple those things together either. Okay, so those are some of the kind of layout or the system design things that that could have been done better. Okay, now the low voltage section over here next to the terminals, that's great. The input power next to the EMI filter, that's great, except for the filters. Like this filter should have been over here, and this one should have been over here next to the flyback converter, right? Just flip those things around. Now the main power for the bulk capacitors, this high power, it is coming up this way, but it could have came around this way and stayed near all the power stuff. Okay, but anyway, so that's something that could have been done better. Now, some of you guys have asked or talked about this current transformer. It has a single wire going through there. Here, I'll show you in this plane. We have a single wire from the board coming through this current transformer. These current transformers, often you can find them at a 50-to-1 ratio, 100-to-1 ratio. So that means 50 turns around some kind of core right here, a donut, a toroidal core, and it's in this plastic housing, which makes it nice to go on the board. Okay, that's a nice current transformer. Those are not cheap, so it's nice they did that. Okay, so the capacitors are holding the bulk supply, right? And then there's a switching transistor somewhere in here, I'm sure, that as it's pulling current from this, it's actually going that direction to the current transformer and then back this way, which that part is a little bit odd. But anyway, it's doing that and it's coming to this. Okay, now the control chip is right here. Okay, so the control chip is right here. It's the SG3525. That 3525 was originally designed by Unitro, so it was a UC3525, but then other people, copied it essentially. And it's a great chip, and it's used commonly. It's been used for years and years. So, but it's a nice package here. It's kind of strange that it's so far away from. Here, let me pull back here. It's just kind of strange that it's so far away from the transformer, the main transformer. It's going to have, this is most likely a transformer for gate drive. So it takes a drive from this, goes through this, and that way it gets isolation from, because if this is all on the secondary side, okay, it's going to drive the power, the switching power, which is on the primary side of the transformer right here. So it's going to be switching that, but boy, it comes from all the way over here, all the way across the board. That is, again, not really ideal. Here, let's go back here so you can see the whole picture. We have our low voltage DC section here to power, our display. It compares the voltage that we're setting on this pot down here to also the current setting. So all these, there's a LM324 op amp down here. So we're doing all this comparison down here to run our output, to regulate the output the way we want, but it's across the board. So the feedback lines wrap around all the way around circuit board like that. So yeah, it just seems to me that the AC power, maybe the display could have been put on this side, all these controls could have been put on this side, and that might have helped change a lot of things. I don't know, but yeah, there is a lot of crisscrossing going on here. You got all this circuitry supporting the display, but yeah, to me, I mean, another way is the EMI filter could have been down here, and it could have came right into the EMI filter. We could add a power switch, say, put the display on this side, put these over here, so the power switch is up here in this corner. So if it's up here in this corner, then we could have ran the EMI filter, all this stuff here, down this way, and had the transformer and that, and then wrapped it back around this way. But yeah, it just seems like there's a lot of crisscrossing to me. I mean, it seems to work well. I think the coupling, we can fix that stuff. Yeah, there's a lot of challenges keeping the voltages and isolations when you're running secondary output power along all this input power stuff where we're supposed to be isolated, running all the way up here, come up here to come to the regulation circuitry. I just think all this stuff probably should have been kept over here and put this stuff over on this side. That way all the low voltage stuff would have been right here on this side of the board. And as far as cooling goes, I think that could have taken a second seat, especially when all the parts are so large. They seem like they're sized appropriately, you know, where they're not going to be running hot and everything's running pretty cool. So I don't think the temperature and the heat sink and that should have taken the first seat of the layout of this board. So that's just what I think. But anyway, just kind of wanted to go share that with you to see what you think. All right, guys. Hey, I hope you found that interesting. And if you want, I think I'd do another video where I take it apart and look at the other converter, the main converter, and see how the power's done. One thing I wish they would have done is put a nicer current pot in there. I have a feeling they thought about it, maybe using the same pot as they did for voltage, but then maybe they missed the power switch kind of being in the way. So then they reverted to using that small pot for the current. I'm not sure if that's what happened, but I wouldn't be surprised. Oh, hey, by the way, I wanted to say thank you to a couple people that have hit that super thank you button down below. So Walter Cheetos 1794, thank you very much. Big thumbs up to you. And P Bay Median, I'll spell them out here. Yeah, sorry butchering your name, but big thumbs up to you. That was really generous. Thanks so much. And you know, for you guys who want to be hit the super thank you button down below, buy me a cup of coffee, that kind of thing. Or there's also the Patreon that you can join for as little as $1 a month. And there's a membership thing down below too. But anyway, thanks very much, guys. And I think I'm going to look at the thermal on this with the thermal camera and post that video real soon. So what do you guys think? Let me know what you think. Hey, I'd like to know what else you'd like to see on this. If you'd like to see some voltage probing, I think I'm going to do the thermal thing just to see how well sized everything. Seems like things are sized really well. But yeah, let's just take a look. The fan doesn't really turn on until it's been on for a while. And it doesn't really feel like anything's hot. Although I'm not going around touching things, I can just kind of feel above and I don't really feel much heat. So the heat sink, you know, put my hand above it, don't really feel much. But I think I'll put a thermal camera on it and post that video. All right. Hey, thanks for watching. And 2 big thumbs up to my Patreons as always. And 2 big thumbs up to everybody watching the video. Appreciate it. We'll see you next time.